minus g L minus d squared c squared over 2v squared s squared Well, with a lot of these things, you just need to plunge in and see where it takes you. If I divide everything by L minus D, I get negative S equals C squared over S minus G L minus D. Because that's D minus L. If you recall, this was negative L minus D, and I just, which I changed into D minus L, and now I'm changing back to my negative sign. All right, so let's get rid of the fractions here. So let's multiply everything by 2v squared s. So I get negative 2v squared s squared equals c squared 2v squared minus g L minus d c squared. V squared, so negative 2 times, okay, so let's solve for V squared. Let's solve for V squared first. So this becomes V squared is equal to, and that over G L minus D C squared over, so bring that over here, this over here, over 2c squared plus 2s squared. Ah, there we go. That looks nice. Which is g L minus d cosine squared over 2. And considering there's so many places to make a mistake, I'm just run through that in my head. So that comes over to the left-hand side, that goes over to the right. So I get 2v squared c squared plus 2v squared s squared. Factor the v out, divide by that, so we're good with that. All right, feeling good? Ish. And that's equal to L minus D, G sine theta.
Wait, okay.
We derived that earlier.
Yes.
L minus D cancels out, G cancels out. So I'm left with cosine squared over 2 equal to sine, equal to sine. All that mess, we're simplified down to this. Cosine squared is 1 minus sine squared is equal to 2s. So I'm left with sine squared theta plus 2 sine theta minus 1 equals 0. Little Pythagorean, quadratic formula. So sine theta is equal to negative 2 plus or minus the square root of 2 squared minus 4 times 1 times negative 1 over 2. So this is negative 2 plus or minus the square root of 8 over 2, which is negative 1 plus or minus, let's see, that's 2 radical 2 plus or minus the square root of 2. We know theta is a positive angle because of the way we defined it. And so theta would be the arc sine of square root of 2 minus 1. Actually, we don't need that. All we need to know is the sine of theta. Plug into here. So D is equal to 3L times the sine of theta, which is the square root of 2 minus 1, over 2 plus 3 times the square root of 2 minus 1. And if we've lived a good life, we will get the right answer. And I guess it will remain a mystery. Correct. Yeah, it would be kind enough, would someone be kind enough to actually calculate that?
Yeah.
What is it? What are you doing? Calculator.
Are we gonna get one like this and that's it?
It's a fun one, isn't it?
Oh, fun, yeah.
Oh, yeah.
Yes.
I thought you discovered something.
I thought someone was working on it.
He's good.
I give up.
I don't know. Maybe I don't know how to put something in a calculator. What is?
Oh.
3 times square root of 2 minus 1 times 3, divided by 2 plus 3 times square root of 2 minus 1.
So you have what, 3 squared root of 2 minus.
Maybe.
2 minus, or 3 squared plus 2.
1.86.
1.86?
Yeah.
1.8.
That's.
L?
If it was
That
done
does,
right.
no, that does not make sense.
Alright.
I got 0.24.
I got 0.38.
All right, we got 3 different answers here.
That's always a good thing.
0.38.
Yeah, that's what I got.
We got 0.38.
Yeah.
Yeah, I got this in this.
0.38.
Something's off there. Three sine, or 2 plus 3 sine. Square root of 2.
I got 0.38 L.
Yeah, something went wrong. Dang it.
We
We
did
have not lived a
live a
good
good
life,
life.
and therefore
We have indeed not lived a good life. Let's see.
We can start from the beginning.
Start from
Not
the beginning.
0.38.
I will assume that you will start from the beginning. See how well you-
Point what? That's very sad. It's like 1.
Let's work this out so many freaking times. So that's just more of repeating the part that. Plus or minus the square root of b squared minus 4 is 2, so that's 8. 8 is 4 times 2, so that's 2 radical 2, so negative 1 plus.
Russell got 0.237.
I got that by putting it in a different way. Something happened.
All right, we're just, instead of just trying to figure out where the mistake is, it's 0.4 something.
Wow,
It's very
round.
close.
It's very close.
It is close.
Yeah.
We will assume that if we recreated that with this, we'd hit it spot on, and so we will leave it there.
Okay.
See if I can edit that video down some. All right, questions before we talk about black holes?
Okay. No, I still got 0.38.
Okay. Somewhere we got a number off.
Just that.
This is right, I'm good with
You
this.
said it was 0.4?
It's 0.4,
I was gonna say, you could round it, I mean, your point,
True, I don't think that's really within the spirit of.
200's off.
0.4641.
Oh,
Yeah, a little bit more.
I was thinking you had like 0.400.
Yeah, no, not.
Just round up. It'll be fine.
It's just rounded to the nearest integer, 0.
What is theta here? Just
44 point.
24.
yeah, it should have been a 35.26 degree angle. So yeah, and work the rest out on your own. It's just it's easy.
Yeah.
All right, so black holes.
I'm gonna talk about how if you watch someone jump into one, you would never see them actually go into it.
It's not convinced you would actually see it, but
Well, if you were able to observe it, you would actually not see them cross the event horizon. They just turn red and you won't.
all right. So if I have some planet here, because we've talked about the gravitational force formula, the generalized formula, the force due to gravity being g m1 m2 over r squared. So if I'm dealing with outer space, I can't really deal with mgh. Mgh works if g, little g, is relatively constant, which is fine if as long as you're near the surface of the planet, but it doesn't work particularly well with outer space. And so if I have some initial position here, we'll call it r initial, and an object's going to be moving out to here, to r final. I know that the work done by the force due to gravity will be the integral of the conservative force dot dr from some initial position to final position. It is moving away from the planet, but the force due to gravity is towards the planet, and so we can simplify the dot product here, since they are anti-parallel, to be negative integral r initial to r final, force due to gravity dr. That's equal to the negative integral of big G, mass of object 1, mass of object 2 over r squared dr. We can take the constants out front, so I got negative big G, mass 1, mass 2 over the integral of r to the negative 2 dr from some r initial to r final. And what is the integral of r to the negative 2?
Negative 1 over
Negative
R.
R.
Negative
1. No, negative. Oh, yeah.
So, say it again, Michael?
Negative R to the negative first.
Yeah.
Or
All right.
Negative 1 over R.
So that negative coming from the integral will cancel out with that one, so I'm left with G mass 1 mass 2 over R from some R initial to R final. And so the work done by the force of gravity becomes G mass 1 mass 2 over R final minus G mass 1 mass 2 over R initial. Because R final is bigger than R initial, this still will be a negative value. I know this is equal to, by the work energy relationships, negative change in potential. In other words, negative U final minus U init plus U initial. So comparing this to that, we can come up with the formula for the potential energy, gravitational potential energy when the acceleration is not constant. And so the potential energy, generalized gravitational potential energy formula becomes negative G mass 1 mass 2 over R. It is a scalar. The negative sign is not an indication of direction. Plus some constant. Now typically, in a problem like this, you let infinite distance away. So when R is infinity, so typically UG equals 0 if R is an infinite distance away. Doesn't have to be, but that's typical. That allows you to just do away with the constant part, or the constant at the end. So what I want to do to figure out the escape speed for something leaving a planet, I want to launch it so that once it is in the air, the only force acting on it is the force due to gravity. So there's going to be something to get it to move, but I don't care about that part. I'm assuming it is hitting the speed as soon as it is launched. It is going away and never returning. Since the only force acting on it is the force due to gravity, it is a conservative force. Energy is conserved. So K initial plus U initial equals K final plus U final. You've done it many times before, so I'll just go ahead and assume that you will say it beautifully if I asked you. Minus G mass, this is mass of the object, mass of the planet over R initial is equal to 1/2 mass of object times final speed of object squared minus big G mass of object, mass of planet for R final. So now we are left with, what can we get rid of?
So from
All right, so it's massive object.
massive object.
We still have the planet, we can't get rid of that.
Well, yeah. Oh, no.
Is one
Pardon?
the final potential since the radius goes to infinity?
Our final is equal to infinity. We can get rid of one more thing.
Why initial equals 0? So we can.
Wait, y initial equals, wait, sorry, what?
Is that y initial? This one. Under the y graph.
That's you.
Oh, you.
Okay.
Yeah.
The gravitational potential energy is 0 at infinite distance away.
Is initial speed 0?
The initial speed is not 0. Because it's being launched. We're trying to figure out how fast do we need to send this thing so it never comes back.
That's it.
So we don't care about the final speed then?
Final velocity. Infinity.
So we
Final
don't,
velocity.
So it's going infinitely fast?
well,
No.
It'll definitely get away.
That's true. I will agree with that.
Infinitely faster.
If you throw something up in the air, does it speed up as it goes up?
Never getting that.
It'd be cool if it did. It'd be cool for like 10 seconds.
Until you tried to jump after it, and then you would go on forever.
That's why I said 10 seconds.
Yeah, like it's increasing to infinity at the radius, so it doesn't even have to keep moving.
so,
It does have to keep moving, but how fast is it moving the farther away it gets?
well, we only care about how fast it is in the beginning, don't we?
Yeah, but we do need to get rid of one more term, actually.
The final velocity term.
Yeah, how can we get rid of this? No.
We don't, because it doesn't matter how far.
Infinity squared is not 0.
Well, it doesn't matter how fast it's moving, because we only care about how fast we need to make it move in the beginning to.
Because
we have to
don't
justify
know-
getting rid of it.
We don't know when it stops, or, I mean.
You're right, we don't know
the
when
rate
it
is-
stops.
Yeah, so
the
like there
rate
is no
is
final velocity.
Infinity.
It should be equal to the initial
Oh,
velocity.
you math people. Where's the physicists in the group?
Darn.
Russell, I missed what you said. Are you the physicist?
Probably not. It should be equal to the initial velocity at
No.
the least.
No, if the final speed and the initial speed are the same, then you probably, and it's being shot directly away from the planet, that means there's no force acting on it.
Conquer the world, broken physics.
No prize.
I mean,
All right, if I throw something up into the air, what happens to it as it's going away from the planet?
well, eventually it tries to equal 0.
As it's going away from the planet, it,
Slows down.
thank you.
It starts
Conrad.
to tilt.
It slows down.
Yeah. So as the thing is being shot away from the planet here, it is slowing down. We're trying to find the minimum speed required in order to launch this, not the maximum speed to launch it. The minimum speed to launch it for something that is just slowing down. So
Oh.
when it's an infinite distance away, it could stop. But it never actually gets infinity, but it's getting slower and slower and slower.
How are we
This is
finding-
close enough to zero, because
Yeah.
the final speed is approximately zero. It doesn't actually equal zero, that's the math people talking. It's close enough to zero to count, that's the physicist talking.
Limit is R equals infinity.
Tricky question.
So what we are left with
One hand VI minus
or equals, just go ahead and add it to the other side. Mass of the planet over,
How we get real massive object on the top?
because every term had massive object in it. So there's a common factor. All right, so VI is equal to the square root of 2 times the gravitational constant times the mass of the planet over, what is RI?
The,
Square.
well,
No.
it's from the surface of the Earth.
Yes, we are judging it from the surface of the planet.
There's the radius of the planet.
Yes. So over radius of planet, radius, I guess I'm using P for planet. And so if we did for Earth, we'd have the square root of 2 times 6.67 times 10 to the negative 11th in SI units, times mass of Earth, which is 5.98 times 10 to the 24th kilograms, divided by the radius of the Earth, which is 6.38 times 10 to the 6th meters. And if someone, concerning that last attempt at calculations, if more than one person could.
Yes.
And the answer is yes, or yeah.
That's what the
I got
calculator
like-
said.
11,181.966.
No doubt, all of it's significant. Units,
Meters per second.
it's, no square, it's.
Miles per hour. That's quite.
Miles per hour, it would be somewhere around 25,000 miles an hour.
So that's escape velocity.
That's escape speed.
That's NASA's cruising speed.
All right, so anything that happens to hit that speed that's heading away from the Earth will go out and it will not come back, assuming it doesn't hit anything else. We are making the assumption that we launch it from the surface of the Earth in this particular example, and we're ignoring air resistance, and it's not gonna hit a bird or anything like that. It's just gonna go up, not gonna hit another planet, just gonna go on forever. So that's the escape speed using conservation of energy. Well, we can take it one step further, because at this point, we know there is a maximum speed.
Light. The speed of light.
Oh.
So from this equation right here, if I let c equal the speed of light, there is an exact value, but it's approximately equal to 3 times 10 to the 8th meters per second. So,
Yeah, close.
Only a little faster.
Or 29.
and so the question is, if we took the Earth, what does the radius of the Earth need to be, maintaining its mass, so that the Earth is a black hole, creates a black hole? Well, we're gonna solve for r there. So r, the radius of the planet, would be equal to 2g mass of the planet over the speed squared, the escape speed squared, and taking into account the fact that there is a maximum speed, this becomes 2g mass of the planet over c squared. In other words, if the Earth maintained its entire mass, but somehow shrank down to that radius right there, nothing could escape it. And so 2 times 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th divided by 3 times 10 to the 8th squared.
Wow,
I
that's
got
not how that's
point
supposed to happen.
0, 0, 887
0.0087,
meters.
877,
887.
8 meters, or 8.87 millimeters. That's the radius. So the diameter would be twice that, which is 17.74 millimeters, or 1.774 centimeters.
The density of that.
It'd be huge. So if the Earth could somehow magically shrink down to the distance, so between my fingers here, it would create a black hole. Not likely. I'm not even sure if it's even possible to crush something into that small a space,
No black
It's
hole
a-
exists?
Yes.
theoretically.
So you're saying there's a chance?
Black
Always
holes
live in
existing
fear.
would explain a number of things, and so the theorists are going, yeah, let's assume there's a black hole there, and they're working with that. To my knowledge, at this point, they still haven't seen any direct evidence. It's not like you would see a black hole. What you would see is radiation coming off of it.
They,
They'll let you the
they
photo
also
of
see
it
stuff like
recently.
manipulating light and stuff like that.
Yeah, they're still.
They're just seeing the absence of something, and they're like, that must be something.
Yeah, which they generally blame on dark matter because you can't see it. So-
Yeah, we have equal dark matter and regular matter, and they should annihilate each other.
All right, let's take this one step farther. Since planets generally don't become black holes, but stars do, let's take a look at our sun. How big does our sun need to be in order to become a black hole? So the radius of our sun, 2g mass of the sun over v squared, which is 2 times 6.67 times 10 to the negative 11 times mass of the sun, which is, always fits in short-term memory, but never. 1.99 times 10 to the 30th. 1.99 times 10 to the 30th kilograms over 3 times 10 to the 8th squared.
How did someone find that value for the mass of the sun?
For the mass of the sun?
Yeah, is that like a universal value?
No, that's the mass of our specific sun. You can do it by, basically what was derived last week. If you know how far a planet is from the sun, and know how long it takes to go around the sun, you can actually calculate it.
That's 3 times 10 to the 4th.
On the bottom, 8.
Well,
It's an 8 there.
I got like 3,000 meters.
Yeah.
2,949.62.
2,949.
Yeah, 0.62 meters.
All right, so about 3 kilometers. Is that the distance from Peters Creek to Hansball? Is that roughly 3 kilometers? So if our sun shrank down to that size, it would become a black hole. Now, we are not expecting our sun to do that.
At least not yet.
No, according to current theories, our sun is not going to do that.
It'll go red giant and then ground dwarf.
So what's going on here, for any of the stars, you got 2 processes going on. You have all this mass trying to collapse in on itself. So you have gravitational forces pulling in, and then you have radiation pressure going out. And so the size of the sun stays relatively the same. Our sun is actually losing mass as it goes, and the fact that it loses energy. And as the hydrogens get together and they form helium, they give off energy. Eventually that's going to run out. Heliums will combine and create beryllium, or hydrogen and a helium will join to make lithium. So as these atoms start to fuse together, you're releasing energy and you end up with less than you started with. It goes up to, I think iron is the last point. Anything below iron can possibly fuse and release energy. But the farther you get away from hydrogen, the less energy that's given off. So as it starts using up the basic fuel and starts going to the heavier elements, the radiation pressure starts to drop, and you start to potentially have a collapse if there's enough gravitational pull. Our sun does not have enough mass in order to do that. What's going to happen in our particular case is the gravitational mass is so small that eventually the radiation pressure will dominate, and our sun will start to expand.
And swallow planets.
Probably not. Because the sun is going to start to expand when its mass starts dropping, because it's giving off energy. What's gonna happen is the sun's mass drops off as the planets will start moving farther out.
Yeah.
So eventually, our sun, according to theory, will be here where we are right now, but the Earth won't be.
Yeah, it'll
The Earth
be,
will be farther out.
yeah, cause it's less dense, therefore less gravitational pull.
Wait, say that again?
It's less dense, with the same or larger volume.
It's not a density issue.
It's both lost mass and expanded.
It is less dense, but the important thing is it's lost mass. As long as you're outside of the spherically symmetric ball of mass, you can treat it like a point mass. So the mass is critical.
In conclusion, the Earth will always be the same distance from the sun.
Well, as long as the Earth and the Sun still exist.
Yeah.
There's a half-hour video, and I think I have a link for it somewhere, which actually talks about what do we expect in the next
5 billion years.
no, even longer. It basically takes it from where we are now to the end of all things.
So like the heat death of the
I think
universe.
I've seen
Yes.
something like that.
It's a fascinating video. I highly recommend it. One other bit. If our sun became a black hole right now, well, we would die, but we wouldn't die instantly.
Problem over.
What would the Earth do if our sun suddenly became a black hole right now? What would the Earth do in 8.5 minutes?
You would finally go dark.
It would go dark, but
Freeze
It
over.
would get cold.
Yeah, like really.
what would, okay,
It would start going like straight.
pardon?
This is what I said that.
What would happen to the Earth's orbit?
Yeah, it would just say, it's just not existing.
If the sun suddenly became a black hole, I'm assuming that the mass of the sun doesn't change, the Earth is still gonna go around just like it has before. It would go suddenly dark, we would be scared probably, wondering why everything went dark. Actually, right now, we wouldn't notice quite yet. Power plants would still run, the Earth generates heat. So
Would it?
we would slowly, eventually everything would die around us and it would last a month. I'm not quite sure. We would know it's coming.
Alright,
Time to riot. No, there's time to riot.
All right. Before you go, I have something to hand back. You don't have it.
I don't wanna.
Test corrections. Please give me your attention. Test corrections. Generally, I want them back 2 weeks after I hand them back, but I think that puts us into spring break. I would prefer to have them before spring break, just so you don't have to worry about them, but we'll just say the Tuesday after spring break. If you do not have them ready at that time and are still planning